This is Dr. Carroll, and today's video is about graph traversals. Now, we've explored traversals with many other data structures, and today we're going to explore the depth first search and breadth first search for graphs. So graph traversals are only going to visit all of the vertices if the graph's connected. If all the vertices aren't connected, then we might not visit all the vertices, and we just need to know that. Another very important high-level thing to keep in mind is that with graphs, if you have cycles, what's that going to do for your traversal? Well, a naive implementation is it's going to result in infinite loops. If you haven't learned by now, those are bad. So how can we prevent this? What can we do? We could mark each of the vertices as we consider it as queued, and then never visit a vertex more than once. If it's in our queue, don't put it in our queue again. So just put it in the queue once, and when we visit it, just visit it once. Okay, those are some high-level things to keep in mind with graph traversals. Now let's look at depth first search, or DFS. Okay, what DFS does is it's going to proceed along a path starting at a vertex V and go as deep into the graph as possible before needing to back up and explore more. That's why it's called depth first. Go as deep as possible first. And this is known as a last visited, last explored strategy. Get some high-level code. So if we had a depth first search method, it's going to start with a vertex V. So if it's not specified in my class, start with the vertex A or 1, the lowest one possible. So we're going to start with a vertex V, and what we're going to do to avoid cycles is we're going to mark V as queued. Now, for different purposes, you can consider this as visited. Okay, so we visited it, it's queued up, we know about it. Okay, well that's great, but now what do? We need to then go down to a vertice that it's adjacent to and explore that. So what we're going to do is for each vertex that is that's adjacent to V that's not been queued, and just to be algorithmic about it, we're going to do this in alphabetical or alphanumerical order. Then we're going to just call depth first search on U. And that's it. That's depth first search. Mark it as queued for each vertex adjacent, call depth first search, and go on that recursively. And that's it. Isn't that beautiful in its simplicity? And there we have it. There's depth first search. Let's look at an example. Here we have this digraph here. And as I said, by default, we'll start with the lowest one. So we'll start with A. So A now is vertex V, and for each vertex that's adjacent to V, which would be B, C, and D, we're going to call depth first search. So we're going to call depth first search on B. Now B becomes our new context, and we're on the call stack, and we're still in the middle of B, and we have yet to do C and D to handle what's adjacent to A. So then we're at B, and we're only considering B, and we do depth first search. We mark this as visited so we don't come back to it. And then for each vertex that's adjacent to B, we're going to call depth first search. So we do that in alphabetical order, so we call depth first search on G. Now we're too deep on the call stack, and we still have to visit H and C and D. So then now we're at G. G becomes our new V. And then we look at all vertices adjacent to G. Oh, we're done. Okay, so we don't even go in the for loop. So then we come back up the call stack. We come back to B. Well, we were in the for loop. We visited G. Now we're going to visit H. You visit H and go there and mark it as queued so we don't get into a loop. And then we consider all vertices that are adjacent to H that are not queued. Well, G has already been queued, so then we don't consider it. We then oh, I'm sorry, we would have considered E first and visited E, and then E doesn't have anything that it's adjacent to, so then we'd come back here. We would then go to F in the for loop and call depth first search on F, and would mark F as queued, and we would try to go to E. We would consider E as an adjacent one, but it's not queued, so we would not call depth first search again on E because it already has been queued. Then we'd come back here. We would notice that G is adjacent but already queued, so then that would complete for H. Come back here, that completes it for B. We come back here, and then we would visit C. Already explored that route. Come back to A, then go to D, and recognize that, wow, this is adjacent, we haven't visited. So to repeat, a depth first search starting at A would yield A, B, G, H, E, F, C, D for this digraph. Okay? And notice if we started at some other location, we'd get a different depth first search. For example, if we started at node F and did a depth first search, we would visit F and E, and that's it, because that's the only part of the subgraph that is connected if you're starting at F, because we have a directed graph here. So that's our example. Now that was our beautiful recursive version. Let's talk about an iterative version. So again, we're going to take vertex V, and we're going to make a stack, and we're going to put V on the stack. We're going to push it on the stack. We're going to push it down. And then while the stack is not empty, then we're going to pop off whatever's on the top of the stack. Now for the STL, pop does not return anything, so I'm just simplifying things here and assuming this isn't the STL and that we could actually get the top vertex from the stack, okay? And when we pop it off, that's when we consider it as visited for the iterative version. And so then for each vertex that's adjacent to W that has not been queued, and we do this in reverse alphabetical order, then we're going to push U onto the stack, and we're going to mark it as queued, and then we're done. Now this is the exact same order of visiting the vertexes as the recursive depth first search. And effectively, the recursive depth first search uses the call stack as a stack, whereas the iterative version explicitly uses a stack. They both use a stack, but the depth first search one uses a call stack to remember where it is and where we're in the for loop, whereas the iterative version uses a stack. Let's work through the iterative version on an example. For example, if we had this directed graph, again, we're going to start at the lowest value lexicographically speaking. So we'll start at biology 2010. We start here, and we make a stack S, and then we're going to add biology 2010 onto that stack. We're going to push it on. We're going to mark it as queued. And the stack's not empty, so what we're going to do is we're going to pop this off. I know we just put it on, but we're going to pop it off, and then we're going to look at all the vertices that are adjacent to it and that have not been queued, and we're going to do that in reverse alphabetical order. So we'll consider exercise science 3830 first, and we'll push that onto our stack and mark it as queued. We'll then we'll then explore biology 2010. We're going to push it onto the stack and mark it as queued. And then we're going to finish the for loop and come back to the while loop. And now our stack has two things in it, so it's not empty. So we pop off this one and mark it as visited. We visit it per se, Then we get everything adjacent to it. Well, that's nothing. And then that finishes the for loop because we didn't go in it. And then we come back up to the while loop, and we pop off exercise science 3080. Notice how it's important that we put this one on first and then this one, because stacks it goes deeper, first in, first out. First in, last out. And so now this was the first in, it's now the last out. We pop it off the stack, and now we get all of the vertices adjacent to it. And we do it in reverse alphabetical order. So we get exercise science 4240, then we push on 4230, and lastly we push on exercise science 4000 because we're doing reverse alphanumerical order. And that's the for loop. And then we come back to the top of the while loop, and we pop off the top thing on the stack. Well, that's exercise science 4000, and then we get everything adjacent to it. We get 4010 and put it on the stack, and then we pop it off the stack. There's nothing adjacent to it, so then we're done with that. So these have been popped off the stack. So now this one's the top on the stack. We visit it, nothing adjacent. This is now the top on the stack. We visit it. We add things that are adjacent to it. Exercise science 4260, and then finish the for loop. Come by the while loop, visit it, and there we go. So to repeat, a depth first search would do biology 2010, visit 2020, then it'd do 3830, and then exercise science 4000, 4010, and then 4230, 4240, 4260. And that'd be the order it visits them in. And that's depth first search. Okay. Now let's talk about breadth first search in contrast to depth first search. So breadth first search is a first visited, first explored strategy. That kind of sounds like a queue, and that's exactly what a breadth first search does. Let's look at the iterative version. We're going to have iterative breadth first search. It's going to start at vertex, of course, and we're going to use a queue. And we're going to push onto the queue. We're going to mark it, the vertex is queued, and then while the queue isn't empty, we're going to pop it off, and at that point it's going to be visited. And then for every vertex that's adjacent to it that hasn't been queued, then we're going to push that onto you, and we're going to mark you as queued. And there we have iterative breadth first search. Hey, would you look at that? That looks very similar to depth first search with one change. Instead of using a stack, a first in, last out, we're using a queue, which is first in, first out. And that's the only difference between the two. Let's see an example of this. Again, back to our letter digraph here. So breadth first search, we're going to make a queue, and we're going to add V to the queue. Okay, so now the queue just has A in it, and we've marked A as queued. So then we come to the while loop. It's not empty, so we pop this off and we visit A. Great. Now we put on the queue everything that's adjacent. We do that in alphabetical order. We add B, we add C, we add D. And then we're done with the for loop. We come back to the while loop, and we say, well, what's the top of our queue? What's in the front of our queue? Sorry, B's in the front of our queue. Okay. Now for B, add everything in alphabetical order to visit, and that would be G and H. Now they're on the back of the queue, and C is on the front of the queue, so we don't visit G or H yet. We come visit C. First in, first out. So we come visit C. We consider adding H to the queue, but we don't because it's already queued. It's not visited, but it's queued. Then what's at the front of the queue? D is at the front of the queue. So we visit D, and then we get everything adjacent to D that hasn't been queued, which is E. So now we get what's at the front of the queue. G is at the front of the queue. E is a lower letter value-wise, but G has been put on the queue first. We go to G, we had everything that it's adjacent to, add it to the back of the queue. That's nothing. Then we go to the next thing on top of the queue. That's H. We add everything that hasn't been queued. That's F. F is now behind E in the queue. Then we visit E, and then we visit F. So to repeat, a breadth first search is first going to visit A, and then it's going to visit all the vertices that are within one step of A, which is B. Then it's going to visit C, and then D. Then it's going to visit all the vertices that are 2 steps away from A, and that's going to be in the order explored is G, H, E, and then 4 steps away is F. Okay, let's see this again just to make sure we got it. A breadth first search on this digraph would explore biology 2010 and then 2020 and then 3830. Okay, that's just like a depth first search, that's fine. But now notice we visit exercise science 4000, then we visit 4230. Breadth first search, depth first search, sorry, would have done 4010. Breadth first search first visits 4230, then 4240, then it's going to visit 4010, then 4260. And there you have it. That's graph traversals.